Okay, today we are learning about factoring polynomials, and one of our vocabulary terms would be to learn what the directions mean when it says factor completely. And so we're going to start with a couple of example problems here. X cubed minus 4x squared minus 5x, right? And so factoring steps. Right? What do we always look for first? We always look for our GCF, greatest common factor. So here it looks like our greatest common factor is an x. So we could pull out an x from all of these terms, and we're left with x times x squared minus 4x minus 5. And then we see if we can factor fully. And so we did do a GCF, but now we need to factor this quadratic. So there's the AC method. A is 1, C is -5. Multiply them together, and then have B here. We need two numbers that multiply to -5 but add to -4. So it would probably be -5 and +1. So our factors will be x minus 5 and x plus 1. So that would be fully factored. We know we're fully factored when we just see x by itself, when we see this linear term. So we're trying to factor to linear terms as much as possible, to the extent possible. Okay, so that would be our solution there. For B, we are going to look at 3y to the 5th minus 48y cubed. Okay. So here we look again for our GCF. We know that 3 goes into 48. We know that y to the 5th has a y cubed in it. So we're going to look at our GCF as 3y cubed. Factoring that out of both terms, we're going to get y squared minus 3 times 16 is 48. So minus 16. Now this is a special pattern. So sometimes we'll look for special patterns. This one is a quadratic. In a little bit, we're going to talk about special patterns for cubic functions. Okay? So this is a quadratic. This is the difference of two squares. And so that factors to y plus 4 times y minus 4. And if you didn't recognize that pattern, guess what? You can still do your AC method. So this is a quadratic where b equals 0. We don't have an x term. We don't have a b. But we do have 1y squared. So a is 1. C is -16. B is 0. So two numbers that would multiply to -16 but add to 0 would be +4 and -4, yielding y plus 4 and y minus 4. So you can always use that AC method even if there's a special pattern. It just saves you time if you recognize it. All right, one more example. 5z to the 4th plus 30z cubed plus 45z squared. Okay, again, always looking for that GCF. It looks like we can pull out a 5 and a z squared. That's going to leave us z squared plus 6z plus 9. This again is a special pattern. This is one of those squared binomial situations. Half of 6 is 3. 3 squared is 9. So this is a special pattern where you're going to be left with 5z squared times z plus 3 squared. And again, if you don't recognize it, you can use your AC factoring for the quadratic. You get 9 here and 6 here, which would be 3 and 3. 3 times 3 is 9. 3 plus 3 is 6. And that would have yielded z plus 3 times z plus 3, which is our z plus 3 squared. Okay, now for the video, what I'd like you guys to do for your video notes, you could be just watching these, but for practice, you should stop the video, practice these problems. Hold on, it's supposed to be 7. Try that one. And that one. And that one. So what you can do is you can pause the video right now, try these problems, they're similar to the examples, and then start the video again and go through the solutions. I'm actually going to continue the video with these solutions. Oh, that's not right. These should both be negatives. This is going to be m minus 1 times m minus 1. So this is where you should land, because you'll get your negative 2m and then your positive 1. Okay, so then we're going to talk about some special patterns. Okay, so for special patterns, there are a couple of what we call difference of 2 cubes, or the sum of 2 cubes, and we have special patterns for that. So remember, this was one of our special patterns for a quadratic, which comes from the difference of 2 squares. Now we're going to talk about the difference of 2 cubes. So here's an example of that. You have to recognize that this is a cube, right? This is x times x times x. And this is 5 cubed. So this is 5 times 5 times 5. And we're subtracting. So we're talking about the difference of 2 cubes. And it has a special pattern. The pattern is you have to identify what's being cubed in each term. And you're just going to write those as a binomial. We're going to have x minus 5. The sign here is minus because this is minus. And then it's going to be the first term squared plus 5 times x, and then plus the second term squared, 25. So if you notice, when you multiply your first term times your first term here, you'll get x times x squared, which is x cubed, and you get 5 times 25, which is going to give you that 125. All the other terms, if you were to multiply this out, will cancel out. Okay, so I'm just throwing this at you kind of quickly, but there's a pattern here. Basically, if you have a cubed minus b cubed, your pattern is going to be, here, I'll write it below, a minus b times a plus a times b plus b times b, which you typically see in textbooks and other formulas as you see this simplified to a squared plus ab plus b squared. Okay, so that's the difference of 2 cubes. Now let's do the sum of 2 cubes. So if we had, in fact, I'll just do the same one, x cubed plus 125 instead of minus, so you can really see the difference here. This time we're going to do that same pattern. The only thing that really changes is the signs that we use. So this is going to be an a plus b, so it's x and 5 So we have x plus 5. Again, times x squared, or x times x. But this time it's going to be minus. We're going to have a negative sign in there. Times, oh, sorry, these shouldn't be x's. These should be a's and b's. A times a minus a times b plus, it's always plus here, b times b. Okay, so this is our pattern. So we're going to have a plus b, a is x, b is 5, times x squared minus 5x plus 5 squared, which is 25. So as far as the signs go here, look, we have the exact same terms because we have x and we have 5, x and 5, x cubed, 5 cubed. The only thing that's different is we have in the first term, the binomial, you're going to have the same sign. The next sign that you see here, when you have this squared, this is going to be the opposite sign of what's in the problem. So the same as what's in the problem. Then the opposite of what's in the problem. And then the last number is going to be an always positive. Okay? So same, opposite, always positive. So same, opposite, always positive. So that's the sign pattern for these. So let's try a couple. Let's try this one. 16, a little more complicated. S to the 5th plus 54 s squared. Okay, so remember, whenever we're factoring, we need to do our GCF first. So GCF, look, these are both even. Does 4 go into both of these? No, but 6 goes into both of these. Is there a higher number that goes into both? No. So let's just pull out a 2, s squared. And that's going to yield 8 s cubed. And then 2 out of 54, that's going to be plus 27. Okay, so now this is 2 cubed. So we've got 8, that's 2 cubed. 27 is 3 cubed. So it looks like this is going to be 2s cubed, right? And this is a plus 3 cubed. So my a is 2s, my b is 3. So when we fully factor this, and we're still going to have this whole 2s business here, 2s squared, sorry, 2s squared here, times, we're going to have 2s plus 3, and then we're going to have 2s times 2s for 4s squared. Then we're going to have 2s times 3, remember our sign is going to be opposite now, 2s times 3 for 6s, and then always positive, 3 times 3. So that should be our full factorization there. 2s squared, GCF, and then our special pattern for our cube. All right. Now, we're going to learn one more pattern, but why don't you try this one first? Let's continue on. And then we're going to learn one more pattern. This was the difference of 2 cubes, by the way. And this one was the sum of 2 cubes. I didn't leave myself enough space there, did I? But this one is the sum of 2 cubes. Okay. So let's do a few more here. We're going to learn another thing now called factoring by grouping. Which is really similar to we use our AC pattern to do this. But let's look at how that looks. So our first step, let's try this problem here. Here's an example here. Z cubed plus 5z squared minus 4z minus 20. Okay, the first thing we always do is look for a GCF, right? Is there a GCF? No. Is there one of our special patterns? No, we don't see a special pattern. So what we're going to do is we're going to go ahead and factor by grouping. And so, in fact, we don't really use AC here. It's part of our AC method, really. But when you use the AC method and you had an A value that wasn't equal to 1, you used a process called factoring by grouping. So all we're really going to do is we're going to look at this first two terms separately from our second two terms. And we're going to factor from the first two terms, and it looks like there's a z squared there. So we have a GCF for our first two terms. And so that's going to leave z plus 5. And then the GCF here looks like -4. -4 and -4 times 5. -4 times z. So we'll pull out the -4 and we'll be left with z plus 5. And I'm going to just cross all these z's because I feel like otherwise my z's look like 2's. Okay, so we've got this. And notice now we have this common term here. So we factor that out from both. And we're left with z squared minus 4. Well, that's interesting because that's one of our special patterns. So we kind of did a GCF here, and now we're going to apply a special pattern. So we're going to have z plus 5 times z plus 2 and z minus 2. Okay, so again, when we reduce it to that quadratic, we ask ourselves, can we further factor this? Or if this had been a cubic, now we know a special pattern for cubes. Okay, and so now we're going to do another type of problem. Do a little line here. This is going to be factoring polynomials in quadratic form. And so what that means is we might have a higher degree polynomial than a squared. Like when we think quadratic, we think of, x squared plus, 2x plus 4, something like that. But when we talk about polynomials in quadratic form, we're talking about higher order polynomials, but that are similar to what we might see in a quadratic. So here's an example. 16x to the 4th minus 81. Doesn't this look kind of similar to, like if this were 16, if this was maybe 16x squared, let me erase this here. If this was 16x squared minus like 49, we'd say, oh, that's a difference of 2 squares. And we'd say, oh, well, that's going to be 4x plus 7 and 4x minus 7. However, this is kind of similar to that, except that this is actually 4x squared. Squared, right? We have a perfect square, and x to the 4th is actually x squared squared. And 81, well, guess what? You might think of that as 3 times 27, or you might think of that as whatever you might think of, but this is really 3 to the 4th power. Okay, so it's a little harder to recognize, but you'll get used to it as you do more of these. So this one, we're going to actually apply our quadratic pattern. And there's actually something we can do called U substitution, which I'm going to show you, substitution. So we're going to let U equal x squared for a second. Let u equal x squared, which means all of a sudden this is going to be 4u squared, right, minus 3 to the 4th. Hold on. Maybe this isn't a good idea. Let's save this for another time. Yeah, let's save this. Let's not do u substitution today, kids. Let's get back to it later. Okay. Skip the u stuff here. Okay. If you think of this as a difference of 2 squares, then what you really have here is you have 4x squared plus 3 squared and 4x squared minus 3 squared. So you can think of all of these as just squared terms instead of oh, dang it. Hold on.